Hi, everyone. Good morning. Although it's evening here. uh, Sorry I cannot be in US, but I hope you can find something interesting from my talk. It's about the construction of hierarchical surface structure on concrete with hybrid nanoparticles for superhydrophobicity. I think Philip's introduction gave a very good starting of my work. And so I will be focusing on the concrete material. There'll be three parts. First is the motivation, and then introduce how the silica-based nanoparticles can be used for surface treatment. And I will introduce the precursor of nanosilica, and as well as the hybrid nanoparticles, then the conclusions. So we all know that concrete structures used in practice always face deterioration. The deterioration always start from the surface, and the aggressive ingredients penetrate from the surface to the inside part of the concrete and deteriorates the whole structure. So the surface protection is one of the most promising ways of enhancing the durability. People normally use the silica-based material for surface treatment because this kind of sodium silicate, lithium silicate, or fluoride silicate has a very good permeable. It's very permeable to the inner structure of the hardened concrete structures from the surface. It will be in-situ reactive, meaning that it will react with the constituents of the hardened concrete. So people always use that. In recent years, people did a lot of research or even the practical use of silica nanoparticles to be added into the concrete for the enhancement of the properties. Due to the high reactivity as well as the fine particle size, it triggers us to think whether these kind of nanoparticles can be used for the surface treatment. And this picture shows the high CH consumption rate of the nanoparticle. So will this feature be taken advantage of at the surface of the concrete? Even some in-situ hydration or reaction can happen on the surface and then modify the surface structure or improve the surface quality of the hardened concrete. That's our interested thing. So to do that, we use the commercially available colloidal nanosilica, which has a size of about 20 nanometers, as well as the precursor, which is the TGA tetrathoxysilane, which will hydrolyze at the surface of the concrete at a alkalinic environment, forming the silica soil. It's a nano-sized material. So we brushed or soaked the these nanomaterials or the precursors on the hardened cement mortar that cured for 28 days, and or soaking the samples in these agents and measure the water absorption and then some other properties. So from this, we can see that a great amount of the water absorption rate can be achieved after applying or spraying or immersing the samples in these agents, and the rate can be reduced to about 40%. Varying depending on the proportions of the samples. So from the carbonation resistivity, for example, here we take the concrete, for example, water to cement ratio of 0.65. We can see the carbonation of the control sample is about 18 millimeter, but after the treatment with the precursor TGA, that can be reduced to about 10 nanometers millimeters. So this is a super reduction of the carbonation depths. So from other like chloride permeability reduction, as well as the calcium leaching resistivity of the cementitious materials. can be achieved after the surface treatment with these materials. And the mechanisms of the surface treatment can be shown by the X-ray diffraction. So from here, from the left, we can see that after the surface treatment with TIOs, that the very inner part of the cement paste, the calcium hydroxide peak, can be potentially reduced when comparing to the colloidal nanosilica treated sample or the control without the treatment. So this clearly show the pozzolanic reaction at the surface after the spraying of the TIOs. And this can be apparently shown by the SEM image. From here, from the silicate element distribution, we can see that the agglomerates of the silica clusters can be found at the surface part, showing that these nanoparticles can fill the pores. Like here, this is about 20 microns, the scale bar. So the pores can be physically filled by these nanomaterials. But when we're comparing these TIOs, for example, here, the water absorption reduction rate to that of the silane, we can see it's still very high. So this triggers us to think whether the hydrophobicity can be combined with the filling effect of the nanoparticles, forming the kind of a hybrid material to take advantage of these two components with one hybrid material. That's a concern. Okay, to do that, we form the so-called the hybrid materials. First is the one component is the silicate component TIOs. It can hydrolyze, forming the nanosilica, and we also use the PMHS. Is a kind of silane, and this kind of silane can be connected with the nanoparticles, forming the hybrid material. So from the characterization, we can see the clear difference between the nanosilica particle here with the hybrid material. So this kind of hybrid material can be characterized by the thermogravimetry, and can see that the detachment of the PMHS is an organic component from the inorganic silica nanoparticles. So this can be used to characterize the content of the material. Let's see the performance that the for the hybrid material, as much as about 50% of water absorption rate reduction can be achieved after this spraying on the hardened mortar sample, and this can be characterized, or can be the reason can be traced by the hydrophobicity. We can see here the contacting angle can go up to about 120 degrees after the spraying of this hybrid material. Moreover, the pore filling effect, can be characterized by the MIP testing. From here, we can see that the characteristic pore size has not been greatly changed, but the volume can be greatly reduced. So by taking advantage of these two characteristics, we can see that after the samples, the cured sample for after 3 and 28 days, we can see that the reduction of water absorption rate comparing to the control sample, that you can see it's increased. So the increase of this reduction, meaning that the effects of the hybrid material, go further. These effects can be more clearly shown after ages. So this shows that the pozzolanic reaction or the chemical reaction happened on the surface. Condensation, compacting of the surface continues to happen with age. So this can be also implied by the pozzolanic reaction with time. 3 days and 28 days, more calcium hydroxide can be consumed with this hybrid material. So you can see, can we, the hydrophobicity can be achieved by PMHS is kind of silane. So can we achieve the superhydrophobicity by varying the components? The answer is yes. So to do that, we selected the FAS, is kind of fluoro type silane, and then by the same way we use the TOs as the precursor, and then the silane as the organic component, forming this hybrid nanomaterial with size of about 100 nanometers, and from the element ratio distribution, we from the in the direction of the diameter, we can see that it's a co-shell structure. And then we can see the performance of this hybrid material. We can see when comparing to the control sample without any treatment, the water absorption rate can be potentially reduced. And this kind of effects can last a very long time by applying the anti-washing simulation. You can see here the washing on water absorption rate of sample treated by different agents. From here, like H160 means 60 minutes of immersion of the sample in the hybrid material, as well as the second one. The second is the silicate oxide nanoparticle. We can see here from 3 days to like 7 days, we can see the water absorption rate decreased. The reduction of this water absorption, meaning that the compaction of the surface continues with age. This is the same case as the one HPMS has shown before. So, moreover, you can see after the application of the nanoparticles on the surface of concrete or mortar sample, the roughness of the surface can be changed. So by using 3D optical image analysis, a hierarchical superficial structure can be achieved, and then this can be more clearly shown by the roughness of the sample. You can see here, control sample is flat, but the hybrid or nanoparticle treated sample, the roughness increased. This will contribute to the hydrophobicity as shown by Philip. So with this, we can see that the superhydrophobicity, which is about the kinetic angle of about 150, can be achieved by this hybrid material, and it will behave better in the UV testing agent simulation work. So with this, I will conclude. The silica-based nanomaterial for surface treatment can greatly decrease the transport properties, optimize the surface composition, structure, and the hybrid nanomaterial show potential for taking advantage of both advantages of organic and inorganic constituents to improve the surface quality. And these two work actually being published in 2 papers. And yeah, thank you very much.